All right, today we're going to dive into a totally different way of thinking about computer architecture. It's a radical shift, and it's inspired by, well, the most powerful and efficient computer we know of, the human brain. We're talking about neuromorphic computing.
So let's just kick things off with a statistic that is, well, it's kind of nuts. When you think about these huge AI models, you'd assume all the power goes into the actual computation, the thinking, right? But get this. For most of our high-performance chips, up to 90% of the energy they burn isn't for processing at all. It's wasted just shuffling data back and forth. The processor is literally sitting there, burning power, just waiting for its next instruction. It's a massive efficiency nightmare, and there's a very specific reason for it.
This whole waiting game creates what you can only describe as a massive computational traffic jam. And believe it or not, the roots of this problem go back decades. And that traffic jam has a name you've probably heard before, the von Neumann Bottleneck. See, ever since we started building modern computers, we've designed them the same way. The processor is over here, and the memory is over there. They're physically separate. Think of it this way. You're a genius factory worker, the best in the world. But every single time you need a tool, you have to walk all the way across the building to the warehouse to get it. It doesn't matter how fast you are, that commute is going to slow everything down and waste a ton of your energy. That is the exact problem that neuromorphic computing is designed to fix.
So, if that old architecture is so fundamentally flawed, where do we possibly look for a better design? Well, it turns out the answer has been right inside our own heads this whole time. Just look at this number, 20 watts. That's it. That is the entire power budget your brain is using to process everything around you right now. It's less than a dim light bulb. Now compare that to a supercomputer trying to do similar kinds of tasks. We're talking about megawatts, millions and millions of watts. That incredible, almost unbelievable efficiency gap is the entire motivation for creating a new kind of computer chip.
And when you put the two approaches side by side, you can really see how different they are. You've got the classic von Neumann architecture on the left, separate processor and memory, always on, always ticking to the rhythm of a clock. Then you look at the neuromorphic approach on the right, and it just throws that all out the window. Compute and memory are integrated, just like in your brain. It's event-driven, which means it only wakes up when there's actually something to do. And it doesn't communicate with continuous values. It uses these tiny, discrete signals called spikes.
Okay, so I've used these terms event-driven and spikes. But what does that really mean in practice? Let's get into the nitty-gritty of how these chips actually speak in spikes and why that's so incredibly efficient.
This right here is probably the best analogy for understanding the core difference. Your standard CPU is like a clock on the wall, just constantly ticking away. Tick-tock, tick-tock, burning energy every single cycle, whether it's doing useful work or not. A neuromorphic chip, on the other hand, is like a conversation. It's completely silent until someone has something to say. It only fires up and uses power when a new piece of information, an event, actually happens. Nothing's happening, no power's wasted. It's that simple, and it's a secret to these massive power savings.
Now, the software that runs on this kind of hardware is called a spiking neural network, or an SNN. Now, a traditional neural network is all about crunching these giant matrices of numbers all at once. SNNs are totally different. They communicate using simple binary pulses, these spikes. So a neuron just sits there and collects incoming spikes over time. And once its internal charge reaches a certain threshold, it fires off its own spike to other neurons. The key takeaway is that computation only happens when and where a spike occurs.
So let's just walk through the process. First, it often starts with a special kind of sensor, say a camera that only tells you when a pixel's brightness changes. If nothing moves in the scene, the camera is silent, no data, no power. But when something does change, a spike is generated and sent out immediately, no waiting around for the next tick of a clock. Then only the neurons that are supposed to receive that spike wake up to process it. And here's the really cool part. Because all this is happening over time, the network can naturally start to pick up on temporal patterns, like figuring out the direction a ball is flying through the air.
You know, this all sounds great in theory, but this is not science fiction. This is real. For years now, some of the biggest labs in the world have been building the actual silicon brains that make all this possible.
So let's meet the hardware. On the left, you've got Intel's Loihi 2, which is a really cutting-edge research chip. And on the right, you're looking at IBM's TrueNorth chip, which was absolutely groundbreaking when it came out. Together, these two chips really represent a huge leap in taking these brain-inspired ideas and forging them into actual silicon.
So let's put them head-to-head for a second. IBM's TrueNorth, which came out way back in 2014, that's an eternity in the chip world, was a monster.
over 5 billion transistors to create about 1 million neurons, all with ridiculous power efficiency. Now, fast forward to 2021 with Intel's Loihi 2, it's built on a much more modern process. The neuron count is about the same, but Intel's big focus was on flexibility, on allowing for more complex learning to happen right on the chip itself, which is why you see a slightly higher power range there.
Okay, I really want this number to sink in because it's just astounding. 400 GSOPS per watt. That stands for gigasynaptic operations per second per watt. What that actually means is that for just 1 single watt of power, IBM's TrueNorth chip can perform 400 times billion brain-like computations every single second. This is the metric that matters in the neuromorphic world. It's not about raw speed, it's about how much useful work you can get done for every drop of energy.
So we have these amazingly efficient chips. Who cares? Why does this radical efficiency actually matter? Well, it matters because it finally unlocks the ability to put powerful, real-time AI in all the places it could never go before, out on the extreme edge.
I'm talking about devices that need to be smart but can't be plugged into a wall or constantly connected to the cloud. Think about autonomous drones that have to react in milliseconds to dodge a tree branch, or a robotic arm that can adapt to an object it's never seen before. Smart speakers that can listen for a wake word for days on end using a tiny battery. Or maybe a wearable health sensor that can monitor your vital signs continuously without needing a charge every night. All of these things require low-latency, always-on intelligence with an impossibly small power budget. That is the world that neuromorphic computing is built for.
So, we'll end with this question. We are fundamentally moving away from an architecture that just crunches numbers to one that processes events in a way that's, well, it's spookily similar to our own neural circuitry. The immediate benefit is clear, these massive gains in energy efficiency. But the long-term question is so much more profound. As we build computers that increasingly mirror the very structure of the brain, you have to wonder, what new kinds of intelligence might emerge?